The focus of this video lesson is exponential automobile depreciation. Example 1. Iman purchased a 4-year-old car for $16,400. When the car was new, it sold for $23,000. Find the depreciation rate to the nearest percent. Since we know that exponential depreciation better models depreciation of an automobile, we're going to start with what we know. We know this will be modeled using an exponential. And exponentials are written in the form, or can be written in the form, y equals a times the quantity 1 minus r to the power of x. We also know that a represents our initial value or starting value of the car. So right now we know that y is equal to 23,000 times 1 minus r to the x. What we don't know is our depreciation rate, r. Now, the awesome thing is they provide us information in this problem that can help us figure that out. We know that when he purchased it, it was 4 years old, and that it was $16,400. So in this particular equation, we know that x represents the years, and we know that y represents the value. So what we're going to do is we're going to take this 4-year-old car, $16,400, we're going to plug those values into the equation in order to determine what r must be. So we have 16,400 is equal to 23,000 times 1 minus r to the power of 4. Okay, now to solve this equation, we are going to isolate the variable r. Now remember, when solving an equation, we always use reverse PEMDAS. So when we simplify an expression, we use PEMDAS. When we solve, we reverse. So the first thing we ask ourselves, is there any addition or subtraction that can be removed? There is, but it's inside the parentheses, so no. Is there any multiplication or division that can be removed? There is, right? This times 23,000. So what we're going to do is we're going to divide both sides of this equation by 23,000. We can't mess with that 1 minus r quite yet, or that exponent, because they're all attached. The 23,000 will cancel. Now on the left-hand side, we have that 16,400 divided by 23,000, and that's going to give us approximately 0.713. So 0.713 is equal to our 1 minus r to the power of 4. Now we're moving up our order of operations. So we've looked for addition and subtraction, we've looked for multiplication and division. Now we ask ourselves, do we have any exponents? And we do, right? That fourth power. The opposite of a fourth power is what we call a fourth root. So we're going to take the fourth root of both sides. On the right-hand side, the fourth root and fourth power cancel each other, leaving us with just 1 minus r. On the left-hand side, we're going to use our Desmos calculator again. So we are going to take the fourth root, and mathematically speaking, I'm not sure if Desmos has the ability directly to do fourth roots, but it probably does. Yes. So if we go into functions here, you'll see this root button. And what we're going to do is type in a 4. And we have the fourth root of 0.713. Now, if you don't have access to Desmos, an equivalent way to do this is to type in 0.713 and then to the power of 1/4. Because mathematically speaking, fourth root and to the 1/4 power are identical. And you can see that by looking at the values here. So we're going to get a 0.92 approximately. All right, so we have here 0.92. Now let's solve this equation for r. So we minus 1, we get negative 0.08 is equal to negative r. Divide both sides by negative 1, and then we get 0.08 is equal to r. So our depreciation rate to the nearest tenth of a percent is going to be 8%. Now, my only concern here is if we've actually got to the nearest tenth of a percent. So let's look really quickly back at what we had here. And if we were to actually round to the nearest tenth of a percent, we actually have a 0.91, and if we round 0.919, so let's see if that alters our answer just slightly. So if we change this to a 0.919, let's see what that does. So if we made that a 0.919 and subtracted the 1, right, we have 0.919 minus 1, we'd get a 0.81. And so really the only difference here is this to the nearest tenth of a percent is going to be an 8.1%. So just a slight difference, but we want to be cautious of things like that because if it's asking for a specific value at a specific level of precision, we need to give that. So we would say here that Iman's car is depreciating at a rate of 8.1% per year. Example 2. A car exponentially depreciates at a rate of 6% per year. Akaya purchased a 5-year-old car for $18,000. What was the original price of the car? So once again, we're going to begin with that formula we use for exponential decay or exponential depreciation. And we're going to plug in what we know. Now, this one's a little different because in this particular problem, they actually give us our rate. So we know that's here, but just keep in mind we have to plug in its decimal form. They do not give us the initial value, and that's actually what's being asked. What is our original price? So the interesting thing is, though, this time they do give us an X and a Y just like before, right? Remember, X is our years, and Y is the value of the car. So we're going to go ahead and we are going to substitute the $18,000 value and our 6% and the 5 years. Okay, now this is going to be a little different because we actually have some stuff that can be simplified over here. So let's go ahead and simplify that. So over here we have 1 minus 0.06, which is going to be 0.94 to the fifth. Now we can actually also simplify that 0.94 to the fifth. So let's go ahead and do that. We'll use our Desmos calculator again. So we have 0.94 and then power is shift 6 to the fifth. So 0.94 to the fifth is about 0.734 if we round to the nearest tenth of a percent. So 0.734. So we're going to say we have 18,000 is equal to A times 0.734. Now we want to solve this equation for A, so let's get rid of that 0.734 that's being multiplied. The opposite of multiply is divide. So we'll divide both sides by 0.734, and then using our calculator, we have 18,000 divided by 0.734. And we see that the original value of the car is about $24,523.16. So 24,523 and 16 cents. So the value of the car when new was about $24,523. Now do note that the steps here were slightly different because of what information was given. Now it's your turn to try. Try this. A car depreciates exponentially at a rate of 5% per year. If the car is worth $30,000 after 9 months, what was the original price of the car? Before you actually try this problem, I really want you to pay attention to the fact that we have 9 months, but that this equation is in terms of years. So be really conscious and really make sure you do the conversions necessary. Feel free to send your answer to me on Teams before you lock it in.